Now let's talk about shear design results. So as we have already checked here, it will show you shear design result at a distance d, effective depth from the face of the support. So shear design results at 417 mm away from the support, start support, and at the end as well, it is showing you a shear force value of 52.39. We have already discussed this particular, that it depending upon your connectivity with the start or end node and depending upon your column orientation, STAAD is calculating based on B, that is your width or depth, divided by 2 plus your effective depth. So here 230 is the width plus 302 is the effective depth. Based on that 417 mm you are getting that particular value. Now currently, to verify the answer, currently I am considering this, let's say 52.39 shear force value I am considering. Now see, this is the shear force that you get from the software, right? That is your actual shear force. Now to this shear force we have to work out the design strength of concrete, that is tau c as well. In your basic beam design you have already learned this, right? Now see, as you can see here, this is the cross section in which we have shown the arrangement of your main bar as well as your stirrups. Now see, your shear force is along the cross section, right? So based on the grade of concrete, now see, based on percentage of steel present in the concrete, your section is able to resist some amount of shear, okay? And if this particular shear force is less than the actual shear force value, then we need to provide the stirrups. Alright, so your percentage of steel that we gonna provide, so that PT will contribute towards your shear capacity. So based on steel present or the provided steel, okay, it has some capacity to resist your shear force, right? Based on the required PT we provide some amount of steel. Alright, now this particular value, that is your shear capacity of the section, is greater than the actual shear force, then we don't require stirrups, okay? So now first of all we have to work out your shear capacity, that is we called as tau c. So let's go with that. Now see, what is tau c? Tau c is the value of design shear strength of concrete, okay? So first of all we will work out that. So either you can follow IS 456 or you can go with the SP16 table, okay? So based on your provided steel that we have provided, we have considered right now two number of 20 bar diameter, okay? And based on that 620 mm square area we are getting, right? So PT for that particular will be 0.87. So based on amount of steel provided and your grade of concrete, this particular table will give you the design shear strength of concrete, right? So you can obtain your tau c value from the percentage of steel and grade of concrete. So based on your provided steel, what is your percentage? 0.87 is the percentage. How I have calculated? Simple, based on provided steel, right, divide by your cross sectional area, multiply by 100 will give you PT. So 0.87 is the PT value, and based on that we can check it over here. So 0.87 will lie somewhere here, 0.8 and 0.90, and we have to look for the M25 grade of concrete. So 0.59 and 0.62 is the value. So we have to interpolate for 0.87 value, right? So I have interpolated the value from here. See, 0.8 for 0.8 tau c value is 0.59 and 0.90 it is 0.62. So if you go with the interpolation you will get 0.61. So 0.61 is the design shear strength of concrete, that is known as tau c. In books you will find this particular notation if you go with the basics. Now see, you have to compare your strength or the section capacity with the actual shear force. But as you can see here, this is the stress, right? Stress in terms of Newton per millimeter square, and we have force in terms of Newton or kilonewton. So either you have two options: convert your force into stress, right? Because we have to compare that particular value with the same units, okay? Or you can convert your stress into force. So here I have converted that tau c value in terms of force. Okay, so we have to compare tau v and tau c. As I told you, right, your shear capacity of section tau c, which we get based on the percentage of steel and grade of concrete, right? So our shear force is 52390 Newton, or we can say 52 kilonewton, right? Now based on tau c value, I have converted that stress into force. So tau c divided by your cross sectional area will give you the tau c value in terms of your force. Simple. So 42.44 kilonewton is the value. Okay, simple. I have to just this value divide by 1000, right? So this is your tau c value, right? So you can observe your actual shear force is 52 kilonewton while the section capacity is 42.44, so which is less than the actual shear force. That means what? You required some amount of additional reinforcement to resist your shear. Now see, if this particular value is higher than this particular force, then you don't require any stirrups. Okay, your shear force will be resisted by the stirrups. If your section capacity is more than the actual shear force, then you don't require additional shear reinforcement, right? And we provide shear reinforcement in terms of stirrups. That's the simple logic, right? So 52 kilonewton is the actual force and section capacity is 42.44. So now what will be the balance shear, or what is the additional shear for that particular? We have to provide the shear reinforcement. So simple, 52 minus 42.44, right? So it will give you your balance shear or the additional shear reinforcement for which we have to work out the shear reinforcement. So 52 minus 42 will give you 9.95 kilonewton. So for this particular amount of shear force, we have to provide additional shear reinforcement, right? If this value is larger, right, section capacity tau c value is larger, then you don't require stirrups. Anyway, as per the codal provision, you can provide the minimum stirrups or the minimum shear reinforcement. Okay, so that's how STAAD is working out the values. Now let's say for this particular force, we are providing two-legged 8 mm diameter stirrups. Now try to understand how the shear force will resisted by the stirrups. Now as you already know, say 0.75d as per the clause 26.5.1 is the maximum spacing of stirrups. So here, as per our effective depth, you get 226 mm. Let's say 300 mm, right? Now let's say for 1 meter span of beam, if I go with the 300 mm spacing, I require 4 spacing of stirrups, right? Plus 1 additional. So that means I will require 5 number of stirrups. Now see, your single stirrup has area of, for 8 mm, it will be pi by 4 d square. If you work out, 50 mm square is the area for this particular ring, right? So your single stirrup can able to resist 100 mm square. Now see, for this particular stirrup, let's say it's 8 mm, right? So your single stirrup or this single leg has area of, if you work out pi by 4 d square, this will be 50 mm square. So your single stirrup has area of 1 and 2. So 100 mm square is the area, right? So based on that, you can work out that particular area based on 2-legged or 3-leg stirrups. Okay, here I have shown the cross section as well. So 10 legs will resist your shear. So based on shear reinforcement requirement, you can cross check that. Okay, now let's move on to the calculation again. Now see, as per the codal provision, if I go with a 2-legged 8 mm diameter stirrup, right, cross sectional area of the stirrup will be 100 mm square. Now see, for stirrup spacing or for the additional shear reinforcement that we get as 9.95 kilonewton, for this particular you have to work out your spacing. So there is a equation in your code. You can refer this clause 26.5.1 for further detailing, right? Based on this, for this particular amount of force I have worked out the spacing. Now STAAD will consider based on this 4 criteria, that spacing of transverse link shall not exceed least of the following. So if you work out your spacing, that is your ASV into 0.87 FYD upon VUS. ASV means this particular, whatever the stirrup you have provided, we have provided 2-legged stirrup, we have provided 8 mm 2-legged stirrup, right? So that area will be 100 mm square. So 100 mm square into 0.87 into Fy into effective depth divided by VUS, that is your force, 9.95. So based on that I am getting a spacing of 1100 mm square. Okay, that is much larger. Now see, again code specify the maximum and minimum spacing criteria as well. So based on this 4 criteria, 0.75D gives you 226.5, minimum spacing criteria gives you the value of 394 mm, and maximum spacing is 300 mm. Your maximum spacing shall not exceed more than 300. So out of this 4 values, minimum you have to choose, that is 226.5. so depending upon this, STAAD is giving you that particular spacing in terms of this 225 mm center to center, right? Provided 2-legged 8 dia at 225 mm center to center, right? So that's how STAAD designs the shear reinforcement as well. I hope this is clear to you how STAAD is calculating the bending moment, and depending upon that sagging and hogging moment requirement, it will provide you the reinforcement detailing. Also we have discussed how the shear reinforcement is calculated by STAAD, and also you can cross check or cross verify these values with your manual calculation. Alright, so it's an easy task. Now as an assignment, what you can do, these are the simple steps that we already learned during the graduation, right? So for this particular simple design steps, you can create your Excel program as well, right? So I'll assign this particular task to work out the manual calculation in terms of your Excel program, so you can develop your own Excel program as well. Okay, so first of all, try to understand the manual calculation, and based on that it will be easy for you to recreate this in Excel. So this will be your assignment to create an Excel program to cross check your STAAD results.